How's it going, Earth Science? We are going to get into some new stuff today. We're going to look at the motion of the Earth, Moon, Sun system, and how that affects our life on Earth here. What we're going to be mainly talking about is these things called celestial spheres. And so, celestial spheres is right where this picture is. It is a representation of what you can see from Earth. And so if we're looking all the way around us and looking above, that point of view, that observation that we can make is essentially like a sphere above our head. Right? We can look all the way in any direction, and then we can look all the way up to the highest point, which we would call our zenith. And we can use this kind of dome-like sphere above our heads to track some objects in the night sky. And so as we go through, we call these celestial spheres. And so this is where anything in the night sky can exist, and we can kind of plot it, track it, so on and so forth. So hopefully we know this. If we think of the sun, it appears to rise in the east and set in the west, all the way across the sky. And so as this happens, we can think to ourselves, well, is it happening because the sun is revolving around the Earth, or is it because of something else? Well, we know that the sun isn't revolving around the Earth, and in fact, it is happening because the Earth is rotating. And so we have to quickly define these two. A rotation is when one object actually rotates around itself, actually turns on its own axis, where a revolution is when one object goes around another object. So revolution is two objects, one circling the other, while rotation is one object spinning around its axis. And so as we have this, a rotation of the Earth is what's causing the sun to look like it is rising in the east and setting in the west. It is looking like the sun is actually revolving around us, but it's not. It's the Earth's rotation. When it's the Earth's rotation on its axis, which we know its axis is on a 23.5 degree tilt, and it takes just about 24 hours for our rotation to be complete, which would be what we would consider one day. Now, it's actually a little bit less than 24 hours, and we'll talk about this in the coming weeks, but it's actually 23 hours, 56 minutes, and 4 seconds. And so you might think to yourself, well, Mr. P, like, where's the extra 3 minutes and 56 seconds? And we'll talk about where that is. It didn't just disappear. Okay? So, now, even though the sun rises in the east and sets in the west, the direction of the Earth's spin is actually from west to east, and its spin is greatest at the equator. Now, this part we've already talked about, but I kind of wanted to just skip over it to show you this picture. So it's going to be moving from west to east. And so as it's moving this way, the sun will appear to rise in the east and appear to set in the west. Even though we know the sun isn't the one that's moving, it's the Earth that's rotating. And we know that the equator, it spins the fastest here because it has the longest circumference to cover. Where somewhere right here has a very short circumference to go around, this one has a very large circumference to go around all the way across. Okay? Cool. Let's move forward. We now know that there's rotation. We've been in outer space. We've taken pictures of the world. But how do we prove that there was Earth rotation? Now, there's two main points. The first is what we call a Foucault pendulum. So a pendulum in general is just something that is swinging. So let's draw it up here. It's just a ball swinging side to side like a grandfather clock. And so as it swings back and forth, we started to realize that if you have a pendulum that's able to be swinging literally all the time, all day long, the pendulum, without you touching it, will actually change its direction 15 degrees every hour. So it'll look something like this, where if it'll start moving on this line, back and forth, all of a sudden in an hour you'll see it start swinging this way. You'll see it start swinging this way. And then all of a sudden it starts swinging this way. And it'll actually continually change direction throughout the entire day. And the reason why it's changing direction around the entire day is But it's actually not. It's actually the Earth that is underneath it, that it's rotating, and the pendulum appears to be moving at 15 degrees per hour. And now you might think to yourself, why is it 15 degrees per hour? Well, if there's 360 degrees in that rotation, and it's rotating over a course of 24 hours, one day, you guessed it, 360 divided by 24 is 15 degrees per hour. And so it changes its motion 15 degrees every hour. Not because it's actually changing its motion, but because the Earth, the thing that we are on, is actually rotating. Okay? The other proof of rotation, we're not going to get too far into it today, because, well, we've already talked about it. It's the Coriolis effect. The idea that things appear to be deflected or curved to the right in the northern hemisphere, to the left in the southern hemisphere, based off of the fact that the Earth is rotating. So as you throw a ball down this way, it's going to actually be curving to the right. And part of the reason is because the equator is moving faster than the poles. Because as you get towards the poles, it is not moving as fast. The object actually gets deflected. No matter where you throw it, it will be deflected to the right in the northern hemisphere, and no matter where you throw it, it'll be deflected to the left in the southern hemisphere. Like I said, we've already talked about this, so I'm not going to go into the Coriolis effect too much, because we've seen it in other units. We've seen it in our weather unit, and so that is just one of the objects, or one of the proof of Earth's rotation. Okay, last but not least, let's talk about this in terms of a larger scale. Like, what effect do we have on this? If it's noon in Plattsburgh, on the opposite side of the Earth is midnight. And so if we have an Earth here, you'll see that if the Earth was, if this was the North Pole, what we are doing is we are looking on the Earth from the top down. And so we're actually looking above the Earth top down, where the center of this circle is the North Pole, and the opposite side of the circle that we can't see is the Southern Pole, and this is like a sphere. But a sphere represented in 2 dimensions is a circle. And so in this sphere, we have a light source, our sun, not drawn to scale, right here. And so we can even give him, let's give him a little smiley face, little sunglasses, you get it? Sunglasses, it's a sun. Bam. Look at that. Now we got a nice little sun right there. So the sun is shining light on Earth this direction. Whoa. And as this light is being shined on Earth, the Earth is going to be rotating so that there's other spots of the Earth that are hitting the light side of the Earth. And so some cities over here that will be moving from the day, or from the nighttime into the daytime. Okay, and so if we know that the Earth is going east, rising in the east, setting in the west, but rotating west to east, what it will look like in this picture is a rotation that's clockwise. From the top down, the rotation would be clockwise. And so that would mean that this city, that's a city that's right here, well, it's about to be moving to a position that's here, here, and here, which means that this city right now is experiencing, if we were to label 6 a.m., 6 p.m., noon, and midnight, this would be the city that's experiencing sunrise. Because it is the first instance where it's actually getting hit by the light. So this would be your 6 a.m. And as it moves here, it's going to be more and more direct sunlight until eventually the sun will be almost above your heads. Which, if that sun is above your heads, well, what does that mean? This is our noon. So we have 6 a.m. We have our noon over here, which would mean this, if this is the sunrise, this would have to be the sunset. Sorry, the stylus I use is still not working. So this would be sunset, about 6 p.m. Sunrise, 6 a.m., sunset, 6 p.m., noon right here, which would mean this would have to be midnight. I know it's one word, but I didn't give myself enough space. So this is kind of where we're going into in this unit. And this is going to be a little bit harder to do together because we're not actually able to be in the same room and draw these out together, but we're going to do our very best, and I'm going to do my very best to simplify it as much as I can. But for right now, that's where we're going to pause, and I will see you next week. Bye, guys.